Okay, so this video is about working with significant figures. This is actually just a support video for what we've already learned in class. So most of this, or hopefully all of this, will not be news to you. So we are going to do some practice around identifying the number of significant figures in any given number. And then we are also going to review the rules associated with doing significant figures and calculations. So significant figures convey precision. I want to be able to indicate how good my measurement device is. So this is the way that scientists communicate the level of precision of their measurement devices to other scientists when they're writing papers and performing experiments and so on. So the three rules that we've discussed in class regarding significant figures, the first of which is that all non-zero numbers are significant. So if I were to look at the number 3, 4, that's a 4, 4, 4, 5, 6, all of those numbers are non-zero. There are 4 of them, so that's going to be 4 significant figures. If I look at the number 4.32 times 10 to the third, I only look at the coefficient of the scientifically notated number. All of those numbers are non-zero, so this is going to have 3 significant figures. The next rule is any zeros occurring between two non-zero numbers are significant. So for example, if I do 4, 0, 3, this 0 occurs between the 4 and the 3, therefore it is significant, so this number would be 3 significant figures. If I had 1, 0, 3, 0, 5, both of these zeros occur between non-zero numbers, so I count them all up, and I'm going to see that I have 5 significant figures. In the case of zeros that act only as placeholders, they have no other job than to act as a placeholder for the number. Those zeros are not significant. So we have 2 examples of where that's going to happen. Let's say that I look at the number 7,000, no decimal place. Well, I need to have the zeros that are present because otherwise my 7 wouldn't be in the thousands place. So those zeros are serving only as placeholders, meaning that they are taking up the space in the 1, the 10, and the hundreds place, so that my 7 is in the thousands place. So in this case, this number is 1 significant figure. Similarly, if I have something that looks like this, okay, again, these zeros are simply there to show me that the 7 is in the, 10,000th place. These zeros don't do anything else except indicate that that's where the 7 is. So again, this number is 1 significant figure. Okay, so if they have a placeholder number. All of the numbers in the coefficient of a scientifically notated number are significant, with the exception of the 10 and the exponent. We actually don't look at those numbers. So like previously when we looked at the number 4.32, the reason I said that what did I say it was, times 10 to the third, right? I don't look at the power of 10 for my significant figures. I'm only looking at the coefficient. So in this case, we have 3 significant figures. So some notes. Sometimes the only way to represent a number with a particular number of significant figures is to use scientific notation. So for example, if I said represent the number 1,000 to 2 significant figures. Okay, well the number 1,000 is this. Right now, those zeros are acting as only placeholders. So this number is 1 significant figure, not 2. If I were to write 1,000 and put a decimal here, that decimal indicates that those zeros now become significant. The decimal shows me that the precision to which I am measuring this number is to the ones place. So this is representing 4 significant figures. So if I wanted to represent this number to 2 significant figures, I would need to use scientific notation. And since the 1,000, right, I'm going to use 10 to the third, my coefficient is going to represent 2 significant figures here. If I wanted to represent 1,000 to 3 significant figures, then I would be able to do this, right? I can always add zeros to show significance. The last significant figure in any number is an estimation. So if I look at one of my examples from above, let's go back to 4.32 times 10 to the third. What I'm saying in this number is that I am confident of the 4. I am confident of the 3. And this is my estimated place value. We talked about this in class. So I've estimated to that point. If I only have a number with 1 significant figure in it, so the number 1,000 only having 1 significant figure in it, I'm actually not confident to any figure. I have 1 estimated place value. So this is no confidence one place estimated. Okay. We also talked about the Atlantic-Pacific rule. I'll do a little bit of a review about that towards the end of this worksheet, but I want to talk first about using significant figures in calculations. So the addition-subtraction rule has to do with rounding your answer to the place that shows the smallest level of precision. All right, and usually that requires us to look at the significant digit, the one that is going to have the fewest number of confident decimal places. So we'll start by looking at something simple like 4.23 plus 5.1. Now, if I plug that number into the calculator, I'm going to get 9.33. But what's happening here is if I look at my first number, I'm confident to the ones place, I'm confident to the tenths place, and I'm estimating to the hundredths place. Okay, so my level of precision in this number is to the hundredths place because it's wherever my last significant digit falls or wherever my estimated value is. In my second number, I'm confident to the ones place, but I'm only able to estimate to the tenths place. So that means that my answer needs to be rounded to the number whose precision is the smallest, in this case, the tenths place. Another way that you can look at this, another way that you can do it if you want to, is by stacking your numbers. And you can see we have in common, right, the ones place and the tenths place, but this number does not have anybody in the hundredths place. So I need to round my answer, right? I guess let me get rid of those lines there. I need to round my answer to this place. So my answer would be 9.33. We've decided that, and that means I'm going to look over here and I'm going to round my answer to 9.3. A reminder about using scientific notation. So if I had numbers that were in scientific notation, let's say 3.9 times 10 to the third and 42. Nope, that's not going to be in scientific notation properly. So 4.56 times 10 to the fourth. I need to convert, I was going to add these numbers together, I need to convert those numbers to the same power of 10 before I can add. So that's what we learned about when we did scientific notation. So if I wanted to do this, I could do 0.39 times 10 to the 4 plus 4.56 times 10 to the 4. And what you'll notice here is if I look at just the coefficients, I actually represent the same amount of precision here. I have confidence to the 10th place estimated to the 100th place. Confidence to the 10th place, I do have confidence in the 1's place as well, estimated to the 100th place. So when I add these numbers together, if I stacked them like I did in the previous example, just adding my coefficients right now, okay, both of these numbers have the same level of precision. They both have numbers out to the same number of decimal places. So then, of course, I'm going to do math here, and that's going to give me 4.95, I think, right? Is that right? That looks great. And then I need my power of 10 times 10 to the 4. All right, so making sure that when you're doing scientific notation, you're adding and subtracting, those numbers are represented in the same power of 10, and then you evaluate the precision the same way as you do without scientific notation. In the case of multiplication and division, what we're doing is we're evaluating the numbers that we're multiplying and dividing by to the fewest number of significant digits. So let's say I have 5.0 times 2. So my evaluation starts with how many significant figures is 5.0, and that's 2 significant figures. The number of significant figures in the number 2 is 1, so my answer must be rounded to 1 significant figure. So 5.0 times 2 gives me 10. Without the decimal, that's 1 significant figure. If I had something that was a little bit more complicated, right, looking at, let's say, 3.693 times 4.2, okay, and I plug that number into my calculator. Let's see what we get. Plug that number into my calculator. 3.693 times 4.2 is equal to, if I just write down what the calculator tells me, it's 15.5106. So if I look here, this number has 4 significant figures. This number has 2 significant figures. The way I've reported this number in this moment, it has 6 significant figures. So right now I'm saying that my answer is more precise than either of the 2 measurements that I've taken. So in order to rectify that, I need to look for the fewest number of significant figures in the numbers that I'm using, in which case that's 2. And I'm going to round to 2 significant figures. So in this case, my answer would be 16. Okay, so that's multiplication and division rules. Just a bit of reminder around the Atlantic Pacific rule, right? So we could do the Atlantic Pacific rule. Right, the way that we're going to use that, let's look at this number 1,000. I look and I say, does this number have a decimal? The answer is no, or absent. If the decimal is absent, I start on the right-hand side, the same side as the Atlantic Ocean. That's why it's A, absent Atlantic, P, present Pacific. Decimal absent, I move until I get to my first non-zero number. I start counting 1, 1 sig fig. If I had the number 1, 0, 1, 0, 0, no decimal, I'm going to start on this side again, decimal absent. I get to my first non-zero number, which is 1, and then I continue counting without stopping. One doesn't matter if it's a 0 or something else. 1, 2, 3, 3 significant figures. Okay. If I have something where there's a decimal present, let's say I have 0.00259. In this case, decimal present, I start on the right-hand side. Start on the right-hand side. I still go to my first non-zero number. I start counting to the right without stopping. 1, 2, 3, 3 significant figures. Let's say I had the number 0.002005. Decimal present, I start on the right, I get to my first non-zero number, and then I continue to count. 1, 2, 3, 4. Once I start counting, I don't stop counting, no matter what side I start from. So, if you want to figure out the number of significant figures, decimal, absent, start on the right. Decimal present, start on the left. Always begin counting with the first non-zero number. And that's for both, right? Whether the decimal is present or absent. You don't start counting until you get to the first non-zero number. And then once you start counting, count everything.